Good afternoon. My name is Mars, and today I'll be talking with you all about dynamic time warping and its applications for comparing CAN data. DTW is an algorithm used to compare two similar signals that have different time lengths. Shown here are two signals that are obviously very similar, but the red begins in a sooner signal than blue, and the blue lasts longer than the red. After applying DTW, the specific landmarks are aligned and shown basically be the same signal. For application purposes, how can this be useful? We took a Class 6 Kenworth truck on 20 drive cycles around Colorado State University to collect some CAN trace data. Shown here is a time lapse of one of those cycles, which normally takes 10 minutes. You'll see us pass through numerous green lights, which on other cycles were red, as well as passing over some train tracks. Luckily, there were no trains passing that day, but we do get stopped at red lights fairly frequently, such as here. After data collection is complete, I turn to my good friend Python for processing and analysis. I have the code plot the initial traces I'm comparing. The two signals are clearly similar, but there's an obvious timing difference, especially around the 480-second mark where cycle blue got stuck at that red light for nearly 2 minutes, while cycle orange was able to continue and complete the cycle that 2 minutes sooner. The code outputs the direct Euclidean distance between the two signals and performs the DTW calculations and outputs both an aligned chart, which shows a more representative drive cycle formed from the two cycles, shown here. It then outputs the cost path it used to compute that representative cycle, which is shown here. Potential applications in the vehicle world include general CAN trace comparisons for development of a nominal cycle, and applying those nominal cycles to fuel efficiency testing, PEMS testing, EV range testing, and detection of various anomalies within the CAN dump. Thank you for your time and attention.